Sorry about that. My ear pods died. So let's pick back up at this next slide. Bonding orbitals have an energy level in between that of the native atomic orbitals that mixed to form them. So this was Linus Pauling's ideas. Let's take a look at the native orbitals, right? The original orbitals before any bonding occurred. These are the original orbitals we expect in a carbon atom. Let's remind ourselves of what they are, right? There's a 2s, it has 2 electrons in it, and there's a 2p, it has 2 electrons in it. That is the native configuration for carbon. Well, how does that change when carbon is going to form a bond? Well, the first thing that happens, or that Linus Pauling theorized would happen, is that the electrons in this s orbital get boosted. They are pushed to a higher energy level, and so that one of them will occupy a p. And the remaining, let's move this p here. One of them will occupy the p. And the remaining electron that's still there would then be at a lower energy level. And while 3 are at a higher energy level, that means the bonds would still be different. So he took his theory a step further and said, no. What should happen in reality is all 4 of these electrons will actually occupy a whole new type of orbital. And it doesn't matter if my arrow's pointing down here. These are all 4 electrons. And the new type of orbital will be called an sp3 orbital. Are these s's? No. Are they p's? No. Each one of these is an sp3, 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 sp3 orbital. Those are the hybrid, the new types of orbitals that are formed after bonding, according to this theory. So bonding orbitals are named for the number and type of native orbitals that made them. So the s portion of the name, right, comes from the electrons that were in the s. The p portion comes from the electrons that were in the p. And then we have a 3, because remember, it was really 3 of these were converted from the p's. So again, he first theorized that one of the electrons was boosted to a p, and then he theorized that all of them were converted. So we have an electron that originated from the s, and then the electrons that originated from the 1, 2, 3 p's. So we have sp3 as the resulting name. The type of bonding orbitals that emerge depend on the electron geometry, not the molecular geometry of that VSEPR theory that we've already learned. So we have to remember our electron geometries, right? Here are some electron geometries for us to consider. If we have a linear geometry, as in this case, the first thing we need to know is how many regions of electrons are there? 1, 2 around the central atom, right? 2. So what kind of hybrid orbitals will be formed? Well, right, according to Linus Pauling, if we had 1 in a p orbital before, and 1 in an s orbital before, then those 2 will combine, the s and the p, and form an sp orbital. These are the names that you'll be asked on a test or quiz. This is what we really have to know. How do we predict what the hybrid orbital will be? And the first prediction is sp. That is the case for every linear electron geometry. It will always form on its central atoms sp hybridized orbitals. Let's see how the trigonal planar example works out. So we have a trigonal planar molecule here. A is the central atom. How many electrons surround it? 1, 2, 3, so 3. Where did those electrons originate? Well, there would have always been 1 electron in the s orbital, Because remember, according to Linus Pauling, any other electrons would have been boosted first. And then these would combine to form one originating from the S, one from the first P, one from the second P. That's an sp2 outcome. That's what we need to predict. Everything trigonal planar in its electron geometry will form an sp2 hybridized orbital on its central atom. How about a tetrahedral? Let's go through that. How many electron regions surround the central atom? 1, 2, 3, 4. That's 4. Where did those electrons originate? Of course, one was in the s orbital and the others had been boosted. How did they come together to form new orbitals? One came from an s, another came from a p, and a p. So what we have now is 1, 2, 3, 4 orbitals. Each one of them is known as an sp3. So sp3 is the answer. Anything with a tetrahedral electron geometry will form sp3 orbitals. Let's speculate about a molecule that looks like this. What if there are 5 regions of electrons around a central atom? And it doesn't matter if they're bonding or non-bonding. Again, electron geometry. So let's count these. 1, 2, 3, 4, 5 regions. So if we had 5 regions surrounding it, and where would those electrons have originated from? One always came from the s. P, P, P. Now, this time, we would have one that is boosted from the d orbital, right? Because there can be up to 5 electrons in d orbitals. And so the outcome would be an s. There can only be 3 p's, p plus p plus p, and a d this time. So our hybridization would be an sp3d orbital. 1, 2, 3, 4, 5. It would be an orbital that looks like this. It's got 5 suborbitals, each one with 1 electron, and they are called sp3d orbitals. Now, how far can this go? Well, the answer is how many, 1, 2, 3, 4, 5, how many regions of electrons can surround a central atom? What's the biggest number you've seen? Probably 6 or maybe 8. That's it. So that's about as high as this can go. And what's the typical number of regions around a central atom? 4, right? Generally it's 4 because of the octet rule. So most atoms have 4 other atoms around them. So the most common hybrid orbital is going to be the sp3 because the most common electron geometry is probably tetrahedral, right? And so that's why CH4 is the classic textbook example. Let's look at how it actually works out for CH4. So before the orbitals hybridize, you've got this circle and these 3 peanut-shaped orbitals that will not come together and make that tetrahedral. So Linus Pauling speculated that the orbitals would actually change. They would have characteristics that are like the S, but also like the P. Part of it is like the S, but also like the P. And that's what a hybrid is. It's a combination of 2 things. And so the outcome is what we see here. A carbon atom is going to have 4 different new orbitals. Each one is called an sp3 hybridized orbital. That will allow it to form that tetrahedral. That explains how carbon can form the 109.5 degree bond angles that we actually do see it form. Here's the outcome of the CH4 molecule. Carbon in the middle, 4 hydrogens on the sides. We see that whenever an orbital from carbon overlaps with an orbital from hydrogen, this in the middle is the bond. So that's 1 bond. Here's our second bond. The overlapping of 2 orbitals, these are our 4 bonds. What if you have a lone pair? Again, the electron geometry is what matters. And so even for this molecule of NH3, you see there's an sp3 orbital because it is tetrahedral, right? That's the electron geometry. And so it's got a bond here, we have a bond here, we have a third bond here, and then the lone pair, right, is a part of its electron geometry. So that's how we knew it was going to form an sp3 orbital. Please take a look at the example problems that I posted on Shobi, and I will see you next time.